Okay, hi everyone. So I am a former student at Masterman, and I was in Miss Smith's pre-calc class, and she's asked me to give a guest lecture on what I'm going to research. I just got my master's in math, and I'm going to get my PhD. So I thought it would be fun to talk to you guys about what I want to do with the rest of my life. Okay, yeah, so the name of this research field is Modular Forms, and it's very interesting to and of great importance to people in mathematics. Um, a guy who developed a huge part of the field and proved this long-standing open conjecture, stated in the 1600s, almost won the Nobel Prize, quote unquote, of math for all his work. Uh, but most importantly to me, and the reason I wanted to really get into the complexities of the subject is because this is a really beautiful field of study that allows mathematicians to tie in lots of disparate areas of math that don't seem to have that much to do with each other. So geometry, algebra, the theory of complex numbers, which I really like because I'm much more of a visual thinker and I like to have a picture in my mind of what the algebra is saying at all times. And it's really nice because it's allowed lots of mathematicians to contribute to this field. And the nice thing is you can translate every single statement in this huge research project, but you can translate it very precisely into a geometric statement about these figures you see on the right called elliptic curves, from its original statement in algebra, which is about finding solutions in the integers to polynomial equations. And statements in linear algebra that have to do with matrices, kind of like the one you see in very rough pictorial form down there. So whatever way you like to think about mathematics, you can think about this whole research field in a way that's natural to you, which is what's so beautiful about it and why so many people have enjoyed studying it for decades now. Right, so like I say, the whole point of this field is that it allowed someone to prove a famous theorem, but I'll get into that later, which is just about solving equations like the ones you see here, finding integer solutions where none of these numbers are zero. So looking for solutions in the integers or looking for solutions mod 2, mod 3, or mod 4. So, reducing numbers mod 2 just means that every even number is 0 mod 2, every odd number is 1 mod 2. Same for mod 3, mod 4, that's all that is saying. That translation into modular arithmetic. And like I said, the wonderful thing is we can translate this problem of finding these solutions into looking at points on these curves here, these elliptic curves. So you see, these are curves in the xy plane. Every point on this curve is a solution to the equations pictured here, right? Every point has an x and a y coordinate. And, there's lots of algebraic structure, right, in the integers, and the numbers reduce mod 2, mod 3, mod 5. It's important that these are prime. So, you can add these numbers, and you can also add points on these curves. And this is a precise translation, not just some kind of fuzzy intuitive one. And you do that just by drawing lines from one of the points to the other, and then, you add them by getting a third point and flipping over the x-axis. You don't need to get into all these details yet or memorize them. I just want to give you a sense of how easy it is to translate these statements. Yeah, and I'll get into that picture at the bottom later. But all of this hinges on the theory of complex numbers, which might not seem that interesting or important to you based on what you've seen. But once you get into undergrad, if you study math, you'll take whole year-long courses in real analysis and maybe just a semester one in complex analysis. But complex analysis is a really beautiful field because everything that seems complicated and involves lots of different tricky cases in real analysis just boils down to maybe one simple case in complex analysis. And all of these things in real analysis where our intuition is wrong, there's some statement just has to be true, but it's false because of some kind of weird example. That doesn't happen in complex analysis. Whatever you think is true almost always is, which really helps in research because your intuition is how you make conjectures and think about things in this whole system that makes sense to you, and then you get specific and translate into all the details and rigorous statements in math and go into proving the tiny details. But the way you make progress in research is by thinking about things intuitively, which is why I love these geometric interpretations. So I am going to tell you about a very important result that illustrates all these connections I keep talking about over and over, and then I'll get into why it's important. But for now, just stick with me because I really want to show you how wonderfully interrelated all these disparate areas are. So there's this main important theorem that was proved in the 90s. And it said that if you have one of these elliptic curves and it is semi-stable, and I'll get into that definition, and there are some associated matrices, and if those have certain properties, then this elliptic curve comes from this process having to do with this picture. Now, I know that seems like a random hodgepodge of statements that probably don't seem very beautiful, but I'll explain. So these elliptic curves, right, are solutions to these equations. Sorry I keep reminding you, but it's important. So these elliptic curves are called semi-stable if, like I say, you can look at equations in the integers, or you can reduce mod something. And generally, when you reduce mod something, lots of numbers become the same number, right? So when you reduce mod 2, all even numbers become 0, and all odd numbers become 1. And the same thing pretty much happens here. So if you instead look for equations mod 2, mod 3, mod 5, mod any prime, lots of points, so to speak, on these elliptic curves will become the same point. And if that doesn't happen too much, there's not too much collapsing of many points into one point, the curve is called semi-stable. And anyway, so if you have one of those semi-stable elliptic curves, for any elliptic curve, you have associated matrices. Like I say, this is wonderful how we can translate these problems into linear algebra, because that's actually way more understood than solving equations like these. Even though solving equations like these looks really simple, and looking at these huge matrices in linear algebra looks much more complicated, couldn't be farther from the truth. Like, just solving simple equations like these in the integers is really hard, and simple problems like this are still open. And of course, solving them in the real numbers is easy, but not in the integers. So anyway, it really helps to translate into linear algebra because we just understand it better. So anyway, if you have these kind of semi-stable elliptic curves, then you have these associated matrices. And like I said, they might have certain properties. For instance, if they don't have this kind of block structure, you don't have the structure where the non-zero numbers are in blocks like this. This is all 0. If you don't have that structure, if the numbers are all spread out randomly, you can't make these blocks with everything 0 out here. These types of matrices are called irreducible because you can't reduce them, right, into these little blocks. And if these matrices have these nice conditions where the trace of the matrix is something specific, remember the trace is just the sum of the entries on the diagonal, you probably remember that. And if the determinant of the matrix is something specific, then the whole punchline here is that these elliptic curves are called modular. That's a special kind of elliptic curve. And right, so if that's the punchline, what does it mean? So this is why I just love these geometric interpretations, because you can think through things so easily and just consolidate all of this information in your mind without remembering tricky definitions. Which really, it's hard to keep track of and remember, and just think about everything visually. It's so much easier to remember. It's hard to remember everything. So anyway, an elliptic curve is called modular if it arises from a certain process, which is actually simple to understand intuitively. So if you have a 2 by 2 matrix, determinant 1, some of them act on this half plane here. By permuting these tiles, you see all these tiles, don't worry about the precise statement. I really want you to take away the beauty and intuitive skeleton of how this all fits together. So anyway, if you have certain matrices of determinant 1, they will act on this half-plane by permuting all these tiles. Okay? And then the matrices that act that way will give rise in some complicated way to an elliptic curve. And the kinds of elliptic curves that arise that way are called modular. So the big punchline here is all of these semi-stable elliptic curves, remember, which are the ones that don't collapse too much when you reduce mod something, all of those elliptic curves are modular. They all arise from this process. And that was the big punchline that allowed this huge long-standing theorem to finally be proved. Yeah, so let's see. Yeah, right, so that was a lot of math. Let's take a little break and hear about the history. Yeah, so like I said, this theorem called Fermat's last theorem was conjectured in the 1600s by Fermat. Funny story about that guy. He actually died in a duel when he was in his early 20s over a girl, but that's a whole other story. But before he died, he made this conjecture. So he said that there are no integer solutions where, all of these numbers are non-zero to a to the n plus b to the n equals c to the n for any number n greater than or equal to 3. So of course we know if n equals 2, there are lots of solutions, right? You just look at a right triangle where all of the side lengths are integers, and you have plenty of solutions for a squared plus b squared equals c squared. But the conjecture made in the 1600s says there are none for n greater than or equal to 3. Conjectured in 1637, finally proved by Wiles in 1995. Yeah. And I should emphasize, it wasn't like he proved this whole thing. So this whole theory I just explained about modular forms and relating all these different areas, that had been built up for decades before by a few key mathematicians who collaborated together, not on everything, but every now and again they'd meet up and two of them might work together on a paper. And anyway, they built up this whole theory for decades, and Andrew Wiles just fell in love with this problem. You can see it's very easy to state. He read about it in some public library when he was, I think, 10 or 11, 12 years old, and just thought he couldn't understand why it wasn't solved, right? And so it just stuck with him. Why can't people solve this? I don't understand. And eventually he went on to study math at the undergrad level and the PhD level. And, he told his PhD advisor he wanted to work on this problem. And the guy said, yeah, that's a wonderful thought, but you can't do it. I don't think anyone will ever solve it. But here's, some related interesting stuff I think you'll really like. It's related. Right, and so Wiles did that. He wrote his PhD thesis in England. I think that's where he's from. But anyway, he moved to the US where he was doing his postdoc at Princeton. And since he had a little more freedom, he had a lot of extra time as a postdoc. You're not taking classes. You're not a professor yet, so you're usually not teaching as much. It's time for you to build up your research repertoire, maybe 1 to 2 years as a postdoc, sometimes more. So anyway, he started working on this problem as, on the side, he was teaching, and but he couldn't get this problem out of his head, and now he kind of had enough background in all this machinery. So he started thinking about it and building up that theorem I mentioned was kind of the final piece to the puzzle. And eventually he realized, after a few years, he thought he'd solved it. And so he didn't want to tell anyone because he didn't want them to steal the proof, or maybe it was wrong and that'd be embarrassing. But he told his best friend at Princeton, also a mathematician, that he thought he proved it. Please don't tell anyone, and please check it. I want to make sure it's correct. So his best friend did check it, and it took a long time. It was like 100 pages. But, he read it, he said, I think it's correct. But, you want to still be sure before you announce something this large to the world. So what Andrew Wiles did is he was very sneaky, so he was working at Princeton. He didn't want to tell anyone he thought he proved it, because, what if he was wrong? So he organized a year-long class for very advanced graduate students. And he disguised this material so that you couldn't tell it was proving this theorem, but he taught this very intricate material, and it had to explain it over and so thoroughly to his students, and had to defend all their questions that, teaching that class should verify that it was correct as far as he was concerned. So he did that. Eventually, the culmination of all this work, he announces he thinks he's proved Fermat's last theorem. It's a huge deal. So, yeah, he's flown out to England, speaks at a conference where, history goes down. He says he thinks he proved it. And then it was just mind-blowing how he said, this is the way I proved it. No one kind of saw this coming. Well, okay, that might be a little bit of an overstatement, but this was a big surprise is the point. No one saw this proof coming from him, or from anyone. And so you're wondering, right, so how was this proved? So, he cited lots of works from others in the past decades anyway. But the whole point is that if there was a solution to this equation, then there's an associated elliptic curve, remember those red curves, and someone proved in the 80s, over a decade of work, that if such curves exist, they're not modular, right? They don't arise from that process of the matrices permuting those tiles. But then in the 90s, Wiles proved, like I said, if those curves exist, then they are modular. That's a contradiction, right? So no such curves exist, because there'd be a contradiction, which means no such solutions exist to that equation, and that proved the theorem. Yep, after 300 years, it was proven, and this guy, Andrew Wiles, almost won the Fields Medal, which is the Nobel Prize of Math. There's no Nobel Prize of Math, pretty much. He would have won it, but he was around 45, and you have to be under 40 to win the Fields Medal, which is weird, but it was originally meant to encourage young mathematicians. That's why there's an age limit. Yeah, so final points. Like I said, hopefully I just want you to take away that however you think about math, you can think about all of math really that way. This field is beautiful and rich and has decades of material from dozens of, just the famous ones, dozens of mathematicians and more. And, there are some people who interpret every statement they interpret in terms of geometry. Someone interprets it all in terms of complex analysis. And the ones who do either are using lots of linear algebra, which is kind of easier, and that allows all these different people to collaborate and just speed this research along. It took decades, but it would take longer otherwise. It's just beautiful and a lot of fun to work on. I mean, it has to be, right, for people to focus on it for 10 years at a time. But anyway, so I wanted to just finally give you guys a link. There's a surprisingly suspenseful, it's like an hour long, but if you're bored during this quarantine, you should watch it. Lightweight documentary, not about the math, but about all this intricate history and suspenseful timeline of this guy proving the theorem and working with, a couple of his friends who also work in the field. And his story of dreaming to prove it since he was 10 years old. And finally proving it. I don't want to spoil too much, but there is a hitch. His best friend checked it right, he taught the course, but then his best friend looked just one more time and realized there was an error in the proof, so it was invalid, right? Like to give you a rough analogy, if the paper, which was actually 100 pages, if it were a 10-paragraph paper, then it was kind of like the 10th paragraph was wrong, the logic was wrong. So not the biggest, most central point, just fell through, but not the tiniest point. It was a problem, a serious problem. And so him and his best friend at Princeton there worked for 2 years just trying to fix this problem because they thought it could be fixed. There was a hole, but they thought they could argue why it wasn't a problem. And eventually they did, and Andrew Wiles cries when he talks about it because no one knew that it was wrong. But finally he realized it was right. He really had proved this theorem. This question of 300 years had been closed. And more importantly, this question spurred on all of this beautiful mathematics, which is so rich, you can spend your whole life studying. Many do, I hope to. And just what a way to go down in history. Yeah, so I encourage you to watch it. And finally, I don't know what students are interested in, so I did want to point out, all this stuff does have some relation to, practical work that people do in computer science. So elliptic curves come up in encryption, right? So there was this whole revolution between private key and public key encryption, where with private key, you kind of can't send anything out in the open over the internet because just anyone intercepting anything you send would let them, decrypt what you sent, let them hack you, so you don't want that. But with public key, it turns out you can send something out in the open over the internet, but it's hard to reverse engineer that information to get what you need to crack the code. So you can do that, it's fine. And then, of course, the person you want to decrypt it, maybe you send something else, this tiny piece of information that does allow you to get back the information you need to reverse engineer that. So you send it by mail, that little piece, your friend can decrypt it, but anyone who intercepts over the internet can't. That was a huge deal. That made life a lot easier. Public key, you can send stuff out in the open. And so the whole that hinges on elliptic curves. The information you send, let me go back. The information you send is you send your friend out over the internet a point P on the curve, a point Q on the curve, and then like I said, you can add points. So you can add P plus P plus P. You can do it many times, and you can look up more if you want online. Anyway, so the idea is that they send you these 2 points, P and Q, and they know if you add P plus P plus P plus P enough times, you get Q. They send you the points, and it is very hard to find out how many times you have to add P to get Q. If you used a computer to try to do it brute force, it might take a million years. It's impossible. That's a secure system. And then, you send your friend over the literal mail a tiny little piece of info that allows him to actually, easily, using the math, not the computer, get back that number of how many times add P to get Q. He can decrypt your message, and your message is safe. No one can intercept it. So that's great. You can encrypt all your bank information. Social Security Administration can ensure no one gets your Social Security number. It's a big deal. And I mean, I think that mathematics is alone reason enough to dedicate time and energy into learning about this field and thinking about it, because it's just a lot of fun. It's really beautiful and intuitive, which allows you to make big conjectures and then, work out this stuff. It's a lot of fun. But anyway, please let me know if you have questions. I'm happy to give you a little more background. I'm still learning about this. I haven't started my PhD yet. Thank you so much for your time, and I think there might also be a Q&A live with Miss Smith. I really appreciate the time to talk to you guys. I want to answer any questions you guys have about grad school or undergrad, studying math as an undergrad. I had so much fun. I got my undergraduate degree at Penn. Then I actually took a year off and took lots of online classes in machine learning and software engineering because I thought that might be a better way to make money and make a living. But then I decided I really, I need to do what I want to do, and in the long term, I'll be financially stable. So I decided to apply for a master's program, actually a PhD program in machine learning. And then once I got there, I transferred to a PhD program in discrete math. And then finally, I realized I really need to do what I want to do. Kind of like Andrew Wiles, or I don't know. I wanted to do pure math, so I decided to leave with a master's in this discrete math program, and now I'm going to apply to pure math programs to work on this area that I love so much, which isn't what I was originally studying. So thank you so much for the time talking to you guys, and I look forward to the Q&A. Thank you so much.